Now we're going to look at finding the derivative of inverse trigonometric functions. So in front of you are the formulas, but we're going to derive some of these. And so we're doing this a little differently than what your textbook does to derive these. I'm going to use implicit differentiation. And so let's just start with the first one. So if I'm trying to find the derivative of sine inverse of x, let's start with this, y equals sine inverse of x. We want to find the derivative of this. Well, I don't know what the derivative of sine inverse of x, but I know what the derivative of sine of x is. So let's use the fact that if we take a composition of a function and its inverse, we just get back that argument, what you're taking this function of, in this case, x. So let's take sine on each side. So sine of the left-hand side, so sine of y is equal to sine of sine inverse of x. So I can rewrite this now. Sine of y is equal to, well, again, composition of a function and its inverse, well, we would just get back x here. So now we've manipulated it so that we can take the derivative of both sides and we would know how to do that. These are both sides that we know how to take the derivative of. And so if I take the derivative d dx of this sine of y, just going to write out that I'm going to do that, and d dx, the derivative of x. So the derivative of the left-hand side, so remember y is a function of x, so we have to use the chain rule here. So we're looking at the derivative of the outer, which is sine. So the derivative of sine, remember, was cosine of the inner. Well, the inner here was y times the derivative of that inside. So derivative of y is 1. But this is y is a function of x, so that's where we had to put that dy dx. Or we could write f prime of x if we wanted to. So that was using our chain rule on the left-hand side. This is equal to, well, the derivative of x is just 1. Okay, so let's rewrite this a little bit. So we have cosine of y all times dy dx is equal to 1. Okay, so let's solve for dy dx. Let's divide both sides by cosine of y. So if we do that, we get dy dx is equal to 1 over cosine of y. Well, we really want this function in terms of x. We don't want it in terms of y. But notice up here, we know what y is. Y is just sine inverse of x. So let's just rewrite that. So we have dy dx. This is equal to 1 all over cosine of y, but y again was sine inverse of x. Okay, so that's not quite what we have right here in our formula that I gave you, right? And so we want to manipulate this not to have that trig function in here. So going back to trigonometry, and you guys did this in that course, we're going to manipulate this, and we're going to use the fact of trigonometric functions and what they are in relationships to sides of a triangle. So let's choose A, or theta, whatever you want to call it, to be this sine inverse of x. We're going to use kind of the same fact that we did up here, where we took the sine of both sides. So let's take the sine of both sides of our equation. We have sine of A is equal to the sine of sine inverse of X. So we know sine of A, composition of a function and its inverse, they cancel each other out, giving us back X. So let's treat this as a triangle. And triangle, remember, our ratio of two sides, so we need this to be a quotient. We could rewrite X as X over 1. So if we make our triangle here, right triangle, has to be a right triangle, and then choose any side to be A, other angle to be A. So it doesn't matter. So let's choose this to be A. So from there, our ratio of sine, remember sine was opposite over hypotenuse. So what my opposite of A is X. Now, this is a right triangle, Pythagorean theorem, to find this side. So we know that 1 squared is equal to, let's call this, I don't know. This is really the adjacent side, so let's call this little a. A squared plus x squared. I want to solve for a, that side. And so let's subtract x squared. I know a squared is equal to 1 minus x squared. Take the square root of both sides. I get a is equal to plus or minus the square root of 1 minus x squared. So now let's look back at this. We're just going to look at the positive. We called sine inverse A. So really, if I can plug this in, this is dy dx, right? Equals 1 over sine of sine inverse of x, which we said was A. Well, we can figure out what cosine of A is now with our triangle. So recall, if you had cosine of A, cosine was adjacent, the adjacent side divided by the hypotenuse of that triangle. So the adjacent side is equal to the square root of 1 minus x squared. So we get dx is equal to 1 all over the square root of 1 minus x squared divided by the hypotenuse divided by 1. So we just showed that the derivative is 1 over the square root of 1 minus x squared. So if y is sine inverse of x, the derivative of y is 1 over the square root of 1 minus x squared. So we can do this with the other trig functions. Tangent is one that you're going to use a lot in Calc 2. So let's derive that one. And in Calc 2, it's been a while since I taught it. You use these triangles a lot to help you solve for values. So you want to get this down if this is something. So let's derive the formula, find the derivative of tangent inverse of x. So we're going to start with what we know. So d dx, that means I haven't taken the derivative yet. So d dx of tangent of x, tangent inverse of x. So let's say we have y is equal to tan inverse of x. And so we don't know how to take that derivative, but we do know how to take the derivative of tangent inverse. Tangent of x. So we want to take the tangent of both sides of our equation. So I'm looking at tangent of y is equal to tan inverse. Oops, sorry. I just said I was taking the tangent of that side. Both sides, tan inverse of x. So doing that, we have tangent of y is equal to x. So we know the derivative of both sides now, so we can take the derivative of both sides. So the derivative of tangent y, we're going to have to use, again, the chain rule, is equal to the derivative of x. So looking at the chain rule, we need to look at the outer function. So derivative of tangent, recall, was secant. This is going to sec the inner piece is y, times the derivative of the inner. Derivative of a y is 1, but it is in terms of chain rule. So we have to, and y is a function of x. So we have to write that dy dx is equal to the derivative of x, which is just 1. So dy dx, let's solve for that. Divide both sides by secant squared of y. We have 1 over secant squared of y. Recall, we usually don't write it this way, but this is the exact same thing as this is squaring secant of y. So we're going to do the same thing we just did, where we're going to treat this as a triangle. So secant of y, let's let that be some angle. So I can call it A, I can call it theta, whatever we want to call it. So let A equal this. Wait a minute. I just think about this because it wasn't the inverse function. Let me just think for a second. Okay, I know what I missed. Y here, we're going to rewrite y what it is, which is tan inverse of x. So this is the same thing then as dy dx is equal to 1 over secant. But y, again, is, y is tangent inverse of x. We're going to choose A to be what this tangent A equal tan inverse. We're going to take the tangent of both sides and then we're going to create a triangle. So tangent of A equals just x. We're going to put it as x over 1. Recall tangent of an angle is opposite over adjacent. So let's set up our triangle. Choose where A is, as long as it's not the right angle. So if we put it down here, and my opposite is going to be x, my adjacent side is 1. My hypotenuse is always across from my right angle. We can figure out what that value is. So I'm just going to call it h. H squared, I know, is equal to 1 squared plus x squared. h then is equal to the square root of 1 plus x squared. And so I can go back in here. I can rewrite what tangent inverse of x is. That's just my value of a. So I'm going to rewrite this dy dx is equal to 1 over secant of angle A. We'll have to think about what secant is. Well, secant is 1 over cosine. Cosine is adjacent over hypotenuse, so I flip it, it's hypotenuse over adjacent. So I know secant of A is hypotenuse over adjacent. So if I look at my hypotenuse, which was the square root of 1 plus x squared, all over my adjacent are my triangles 1. So now let's just go back in, replace what secant of A is in here, and we have the derivative. So the derivative, so d dx of tangent inverse of x is equal to 1 all divided by secant of A, which we just said was the square root. Oops, we're not done. I forgot one little piece. I was thinking this is not right. Should be squared. This should be squared because of this square here. So this is going to be squared. The square root of secant of A, which is the 1 plus x squared. Squaring that gives us 1 all over 1 plus x squared. Which, if we look at it in that formula, was 1 all over 1 plus x squared. Okay, so our example is y equals sine inverse of 1 minus t. So we did just derive this formula. And in our case, this value of x is 1 minus t. So if I look at the derivative of y, so y prime is equal to 1 all over the square root of 1 minus x, but our x value in this case is 1 minus t, quantity squared. I wouldn't expand things, and I want you to make sure that you don't do this. Square root of a squared plus or minus b squared, we can't break that down because of the addition and sum in between our terms. This does not equal a plus or minus b. If that was multiplication or division, then we can use that a rule and break it down. But addition or subtraction in between squares and taking the square root wouldn't break it down. Okay, well, let's say again, you didn't memorize that formula. You didn't want to derive it. I mean, we could derive this just as fast. We can do our implicit differentiation. So we could take the sine of both sides. So sine of y equals the sine of sine inverse. That would just give me 1 minus t. I would go then and take the derivative of both sides of my equation. Well, derivative of sine I know is cosine of my inside y times the derivative of my inside is dy dt equals, because y is a function of t, not x, derivative of 1 minus t. In this case, derivative of 1 is 0, but derivative of negative t is negative 1. So dy dt, this is equal to negative 1 all over cosine of y. But I know y is the sine inverse. So this is equal to negative 1 all over cosine, but y is sine inverse. 1 minus t. I can now choose my a value to be sine inverse of 1 minus t. I can take the sine of both sides and then create my triangle. So sine of a is 1 minus t. We want to think of this as a quotient, so all over 1. Sine is opposite. So my opposite value is from this value of a would be 1 minus t here over hypotenuse. Let's call this little a for adjacent. So to find my adjacent side to this angle A, again, using Pythagorean theorem, I know that that's going to be it's equal to 1 squared, which is 1, minus 1 minus t quantity squared. I kind of skipped a step there. And so now I'm going to go back in. I'm going to plug this in. This is my a value. So I really want negative 1 all over cosine of a. Let's use our triangle. And so cosine of a, cosine is adjacent. So this over hypotenuse, which is 1. So this is negative square root of 1 minus t quantity squared. All over 1, but I don't really need that. So that was the derivative of this sine inverse. I need a t there. Of 1 minus t. Which is the same thing. I know it was a lot longer that we got right there. But it was done without having to memorize that formula. And I might ask you, it could be a good question to have you derive how they get one of these on a test.